So this is our third Alumni Spotlight event, and during these events we shine a light on the expertise, the passions and the careers of our vibrant alumni community. Today we're being joined from alumni from 21 countries, including the USA, Australia, China, Indonesia, India, all over Europe, the UK even, of course, and Qatar, and from all 4 college faculty. So a big welcome to everyone, wherever you are, whatever time you're at. So for the next hour, we'll have the pleasure of hearing from Dr. Veronica Bray Durfey. She's had a fascinating career since graduating from Imperial in 2009 with a PhD in Planetary Science, and you'll hear all about that during the event. Earlier this year, she was the recipient of an Imperial Emerging Alumni Leader Award, and we were just really inspired by her achievements in just over 10 years, including being one of just 2 international collaborators on the New Horizons mission to Pluto, and an exciting role model to the children she meets through her outreach work. To chair the event today, we are delighted to be joined by Professor Gareth Collins, Professor of Planetary Science in the Department of Earth Science and Engineering. Has to be one of the most exciting departments, I think, at Imperial. Gareth played an instrumental role in Veronica's time at Imperial while she was studying for her PhD. So he is the perfect person to be facilitating this talk today. So before handing over to Gareth, I just want to have some housekeeping. So we like this to be interactive. So if you have questions, please ask them at any time through the Q&A function. That's the Q&A chat button on your screen. And so we will be inviting you to thumbs up to the ones that you really like. And we ask the ones that get most thumbs and are most popular in priority. But we'll try to get through as many questions as we can in the hour we have together, and we'll sure that you'll get your question asked. This is being recorded, so please don't give away any personal information in your questions unless you want to, of course. And just in case we don't get to every question, Veronica has very kindly agreed to write answers to any unanswered questions after the event. So as a perk for alumni joining us, we will post these on our alumni platform, Imperial Plexus, in the coming days, where you'll also have access to the recording. So over to you, Gareth.
Thank you, Nicola, and hello everyone. I hope you're sitting comfortably and looking forward to a fascinating discussion this evening. For those of you that don't know me, my research investigates the many and varied consequences of what happens when space rocks collide with planetary surfaces, and I do that by developing and applying computer simulations. I'm very excited to be joined by Veronica today. Veronica was actually the first PhD student that I supervised when I was a research fellow over 15 years ago at Imperial. And I've followed her career ever since with great interest, and I must say a great deal of pride as well. Veronica's PhD thesis, which I said she did with me, looked at a detailed comparison between the impact craters on the moon, like the one that you can see behind me, and those that we see on the icy satellites, principally Ganymede and Europa, the 2 of Jupiter's moons. And by comparing those observations between the moon and icy satellites, she was able to both develop a numerical model for how the impact process proceeds in icy bodies, but also to start to use craters as a way of probing the subsurface, a way of learning about what's inside a planetary body by looking at the craters on its surface. And we'll talk more about this a little bit later. But first of all, hi Veronica, how are you doing? Where are you in the world, and what time is it?
Hi Gareth, I'm in Tucson, Arizona in the United States, and it's 10:37 in the morning, so natural lighting.
Yes, very good. Yeah, great. Well, so glad that you could join us today. And I know we've got lots of people who are dying to ask you questions. But if it's okay, I'll start with a few questions of my own. And I thought that as we've got hopefully some younger members of the audience, I'd start by asking you, did you always want to be a planetary scientist?
Yes and no. I wanted to be a planetary scientist from the age of 6. So really lucky to know what I wanted to do. It was after seeing the images come back from the Voyager probes, going past Uranus and Neptune, and wanting to work out why the planets were, why did they look different? What was the cause of that? Although I wanted to be an actress and a drummer between the ages of 8 and 12, I think. And then at the age of 13, I had a really good science teacher, Mr. Noble, who he dropped some alkali metals into water, and the whole class really enjoyed the explosions, and it really got me turned back towards science again. So yeah, I've always known, and it has really helped me organize. If you know what you want to be, you know what you need to do at university, therefore you know what you need to do at A-levels, and I even chose my GCSEs specifically. So that was very lucky. I don't think many people have that head start to know how to plan, and it also allowed me to work on whatever my weaknesses were. I was terrible at maths, and so it definitely showed me that I needed to work on that. And I was lucky enough that my mum could organize a tutor for me and helped me with all of my subjects, because I was a C/D borderline student across the board. Before tutoring helped me to just slow down my brain and write down all of my workings, and it helped me just to apply common sense if I didn't know the answers, and it brought my grades up. I do think it's important to note that the work that I do now with the high-rise camera, there are 5 of us that target the high-rise camera and take pictures of Mars. 2 out of the 5 of them started off with music degrees. So not everyone that ends up doing what I'm doing had this plan since they were 6. You know, a lot of people come to it later on and through very varied paths.
Yeah, so I think that's one of the great things about planetary science, isn't it? That there's a home for everyone in planetary science, and it's such a multidisciplinary subject. So great. So let's move on then to talk a bit about your PhD. So yeah, tell us a bit more about what I sort of very briefly sort of mentioned at the beginning, about what you learned about comparing craters on the moon with these amazing images that were taken, you know, long before you sort of knew that you wanted to be a planetary scientist. So
I did use Voyager data and Galileo data that was taken way back when I was first starting to pay attention to it. And so it was amazing to then use that as part of my thesis. So I would use the Galileo and Voyager images of Europa and Ganymede. Both of these are 2 of Jupiter's largest moons. And I was trying to get an idea of what the impact craters look like on the surface. And then, of course, joined forces with you, and you trained me up on hydrocode modeling of the impact process so that I could start trying to recreate those craters. So I would set up my simulations with an ice layer over water, which is what we think we have at Jupiter's moon Europa. And I would vary the heat flow through that ice crust and the thickness of the ice crust. And then when I simulated impact into it, it would give me a crater that didn't look like reality if my ice shell thickness was wrong, or it would give me the correct crater morphology if my ice shell thickness and my heat flow was a good representation of what we think is going on. So it allowed me to get an estimate of how thick Europa's crust was.
Yeah, so a really sort of powerful sort of demonstration of how we can use craters to understand the subsurface. But why do we care? Why do we want to know what the thickness of Europa's crust is?
It has implications for how habitable it might be. There's a selfish for human beings reason in that if the ice shell is thinner in some areas, then we'll be able to reach that water more easily. And that's important for things like rocket fuel. And also we need water to survive. but also for the development of extraterrestrial life. The Europa is one of our hot places for the possible evolution of life there that has nothing to do with Earth. And some people have suggested that if the ice shell is too thick, you wouldn't get overturn of the crust, you wouldn't get the transfer of different oxidants and things from the surface down to the ocean. So having a thinner crust makes it more likely that life could have evolved on Europa.
Yeah, fascinating. So yeah, tell us a little bit then about life at Imperial back then when you were doing your PhD.
A whirlwind, a complex whirlwind, because as you know, Gareth, I started my PhD originally with Professor Joanna Morgan, and it was going to be looking at the Chicxulub impact crater, which is what we think is left over from when the dinosaurs were killed off by an impact. And so my first year at Imperial included some field work in Mexico. And compared to my usual sit at a desk and look at images, that was hard manual labor, hacking through undergrowth with machetes, dragging a baby bath full of water and cement behind us, digging holes and fitting seismometers as part of Joe's Chicxulub seismic experiment. But then in order to investigate Chicxulub, I needed to be trained up on the hydrocode with you, and your project was icy moon impacts. And I loved that so much that I ran off into the outer solar system with you. And most of my days became a little bit more, at my desk. It was very nice to have the setup that Imperial had. I had 6 pod mates. We had a pod of 6 desks in the large PhD room. And the people in my pod would be, the people I had my lunches with and went down the pub with afterwards. And you could get a lot of, not research, but you could get a lot of scientific discussion and thinking, like after hours and over lunch. So it was very nice to have that kind of friendly feel to the department. And I think the department really helped with that, with our, I don't remember if it was 10 or 11 a.m. tea and biscuits. And as a poor student, you'd squirrel away as many chocolate digestives as you could in your napkin and carry them back upstairs to your desk. Outside of that department bubble, to try and get a bit of work-life balance, my main friends during that time were the archery group. Imperial College has a very good archery club, and I'd shoot with them most days. And especially during the summer, this was a really excellent break in what could be hard-working days, because I could come out of the Royal School of Mines, go across the road to the Royal Albert Hall, and then walk through Hyde Park to Kensington Palace Gardens. And we had a special key to get us into the gardens, and we were allowed to shoot there with the agreement that when the royal family needed to land their helicopter, we would put our bows down and step back and allow the landing. So that was good to try and maintain, because the PhD, there's a lot of work and a lot of effort, and you can do that in a measured fashion. Like one of my pod mates, Caroline, she finished her PhD early, and she was very regimented with her timing. She did a little bit every day and really got it done well and calmly and on time. And the rest of us did it in a more, the flailing is the wrong word, but in a lot more of a sporadic fashion with sudden crunches before deadlines. And then, took a few days off afterwards. But everyone's different. And so if you get the job done, it doesn't matter how it was. But it was, a lot of work hard, play hard feeling from PhD.
Indeed, I'm sure there's a lot of people watching that can relate to that, a lot of those stories. Thanks very much for those. So then after you left Imperial, you're obviously in America now. Is that where you've been ever since graduating from Imperial? Tell us a bit about what you did next.
So I was lucky enough to get a smooth transition from PhD straight into a postdoc job. And to take the opportunity to embarrass you slightly in public, Gareth, this is direct thanks to you and Joe. I forgot to mention when we were talking about my PhD time, the second year of my PhD, Gareth sent me over to Arizona to the Lunar and Planetary Lab to work on the Cassini mission with Professor Zibby Turtle, and to get me seen, get my foot in the door. And Jo Morgan made sure she was able to fund me for some conferences so that I could go around and be seen and get to know who's doing what, and importantly, where the jobs were. And so that was really helpful. And it allowed me to applied to a couple of postdocs. And also during my PhD, I wrote a proposal to NASA to fund my future work section, all of these questions that had come up during my PhD work. And that was to work with Jay Melosh, investigating a particular type of crater on the icy satellites and on Mars called central pit craters, which at the time were thought to be just to do with the presence of ice. So they were a really important prospecting tool. But as you know, it takes a long time for a research proposal to be reviewed and accepted, and for you to know whether you've got that money. So while I was waiting to hear about that, I had to accept, not begrudgingly, I don't want to say I had to, but I'm risk averse. So I applied for and accepted a position working on lunar and Martian data with Alfred McEwen, also here at LPL. And then 2 weeks later, I got the funding through that I'd requested. So my postdoc was spent juggling 3 different projects on the Moon, Mars, and icy satellites.
Wow, doing 3 jobs at once. That must have kept you very busy. So what was your highlight of that first sort of study where you were looking at craters on the moon and trying to understand a little bit more about the impact process from those amazing images that were coming back at the time?
So I've set up with Corinne a couple of pictures that are my favorite from.
Okay, great. Corinne, can we have a look at those?
So the impact process is so energetic that it's got more energy released than nuclear bombs, several orders of magnitude different for the largest impacts. And so it's so energetic that it can melt rock. And so we see with fresh craters on the moon, we see a lot of impact melt inside the crater and around the crater. And my projects with the Lunar Reconnaissance Orbiter camera, which is what the images in front of you're seeing, that they're from LROC, I was looking for these impact melts. And this is one of my favorite images. In the top left, it's Giordano Bruno crater, which is one of the freshest 21-kilometer craters on the moon. And so it has a lot of impact melt textures still there. And we were expecting things that look like lava flows, but this pool of impact melt that deposited just at the base of the crater wall inside the crater, we were not expecting to see this swirl of impact melt that solidified as it was moving. And in that zoomed in picture, you can really see this spiral pattern. And this was first discovered by a student that was working with us, Christy Cordell. And I thought it was an April Fool's joke when she called us in. I thought somebody had photoshopped something funny. I was not expecting to see this. The next picture is another picture.
So does that tell us something about how hot the melt must have been, or it looks incredibly sort of fluid.
Yes, impact melt is superheated, hotter than terrestrial lava, and so it is very fluid. It moves in a low viscosity fashion. It sloshes around closer to water in its movement, and then as it cools in the really frigid lunar environment, you can have this morphology, like the swirls frozen in, because it can cool so quickly at its surface. And what we think created this swirl, we see kind of bathtub rings around it. And I was never sure whether this swirl pattern was created by incoming impact melt kind of sliding down the crater wall and giving it a push and swirling it, or whether there was drainage occurring and it was more like a bath plug, like a bathtub plug being pulled out and going down the plug hole.
Great. And so you started to sort of get involved in sort of missions at that point, sort of directly by looking at these missions. And so is the moon kind of where you stayed, or did you go exploring after that?
Oh yes, all over the place. That's the benefit of having done a PhD in impact cratering, is it didn't limit me to any particular body. Everything in our solar system is hit with asteroids and comets, and it's one of the reasons I chose the PhD. So I did go planet hopping. I always come back to the moon and Earth for my comparisons, because they're the bodies that we know the most about. Like, we can actually get hands-on on Earth impact craters. And so my other research has started looking at impact craters on Mars, looking at the subsurface layering that is exposed, how much ice we think is in the subsurface, and also still always the icy satellites. I seem to find myself always coming back to icy satellite work, and the mission involvement that I've had has really helped me get back there. So I was part of the LROC mission as a team scientist, and also part of the targeting action team. So I wasn't one of the mission operations people actually targeting, but I did suggest the targets. So Giordano Bruno was like one of these craters that me and other people suggested as a target for the LROC, which is the Lunar Reconnaissance Orbiter camera. I then got into mission operations work. In 2011, I started training up with the HiRISE camera to take images of Mars. So it was really, really good to get to be behind the camera, as well as using the data that came back from it. And because I kept my 50-50 science and mission operations, it's allowed me the opportunity to start getting into mission design, because I now have the opportunity to share that mix of experience, like science and mission operations. So, as I said, I've found my way back to the icy satellites, and my newest mission involvement is helping to develop a seismometer for a potential Europa lander. And we're currently in development, and fingers crossed, we're not the only seismometer in development for this mission, but I'm hoping we have a good shot.
Great. This all sounds fascinating. So many questions I could ask you, but in there you talked about getting back to where I think your passion really lies, which is in the outer solar system. And I think the vehicle that got you there, right, was New Horizons. And this, I think, of all of the things that you've done in your career that I've followed, this sounded like the most sort of exciting. So, yeah, tell us a bit about that.
So New Horizons will be hard to beat. it was a stressful time during my postdoc that I was juggling Mars, the moon, and the icy satellites, but that inadvertently was training me up as a comparative planetologist. So just a name for somebody that looks at the different planets and compares them, uses examples of what we know goes on the moon and Earth to inform what we see elsewhere. And that mix of knowing about both rocky and icy bodies was really useful. And one of the reasons I think I was chosen to be one of the 22 members of the New Horizons Geology and Geophysics investigation team. We do have some pictures from this.
Yeah. So when you before you saw the first pictures coming back of Pluto, what were your expectations? Were you expecting to see something like the moon, something sort of just full of craters, but otherwise rather dead?
Oh, yes, that's exactly what I was expecting, and the whole team was really split on this. Some people were expecting activity. I was just expecting an icy body with a lot of craters on it. I wasn't expecting activity. And so I'm used to dealing with orbital missions. So if you take an image and it's not, some clouds got in the way, dust got in the way of like a Martian image, you can always do that again next week. And so the New Horizons mission to Pluto and beyond into the Kuiper Belt is a flyby mission. You only get one shot to get that image, to get all of that different data that you're asking for. So it was a very nerve-wracking. And of course, it doesn't communicate with us while it's doing its flyby. It's busy recording all of this data. And we had to wait, I think it was a 13 hours of silence from the spacecraft while it was busy going through the Pluto system. And we didn't know whether it was going to crash into anything. We didn't know whether we'd missed a small moonlet or a ring or something. And so it was very stressful to be part of a flyby mission. And it was very strange to be part of an active mission that was so publicized, because all of that stress and apprehension of whether we got through the system safely and whether we were going to get any data back was recorded. And so there was one of my favorite pictures, not my most favorite, but one of my favorite pictures from the encounter made it into an Italian newspaper. And it was just me looking at my watch, looking frantically worried because my watch was a bit fast. I always set my watch a couple of minutes fast. So I thought we hadn't received the call home signal. And so that had implications for the life of the spacecraft. But a benefit of having those photographers in your face all the time during the mission was that when you forgot about them, and they were very good about trying to blend into the background, eventually they just became part of who was in the room with you. They started to get pictures like the one that's on the screen at the moment. And this is when the first full globe image of Pluto was revealed, the New Horizons science team. And it was wonderful to have this caught secretly on camera, because this is the moment that I fulfilled the ambition that I pictured in my head when I was 6. And I don't know why I pictured myself in a dark room. Maybe I saw something on TV, but I always pictured being in a dark room and seeing an image of somewhere not imaged before for the first time, and it's just you and that planetary body. And so in this case, they had turned the lights of the room dark so that we could see the image properly. And after the reveal and the applause and the wows, we all immediately got up, and we could have brought it up on our computer screens to, get a close-up look, but everyone was so impatient, we just crowded to the front of the room and started pointing at what we were seeing and discussing what we were seeing. And if we go to the next slide, please. it can show everyone else a picture of the image that was revealed to us. So,
so is that the first time that you weren't pointing at a crater, or were you pointing at a crater?
No, I think we were pointing at what everyone else sees when they look at Pluto, and that's the heart. Like,
Yeah.
what on earth is that? And the people on the team that are volcanism is their speciality. Of course, they see lava flows and volcanoes, and for me as an impact person, of course, I see a very large impact basin. Oh, sorry, can we go back to the colored photo of Pluto? So the image that we were presented with, this one right here, was our fail-safe image. It was the last image taken by New Horizons before it flew through the system. So if it had impacted into anything on the way through, this would have been it. We wouldn't have seen any more close-ups, but we would have had this great global picture.
And this would have been enough, right, for that mission. Yes. This is just such a spectacular image. So what is the heart?
So the heart is, at the moment, we think it was the result of a very large impact. So one that plowed in from the south. We might go to the next picture, actually. Oh no, never mind. Let's stay with this. We think that there was a large impact basin that created a cold trap so that the atmosphere of Pluto could condense into it. So this gigantic impact basin then started filling up with nitrogen ice. So once it reached a certain thickness, it then started convecting, and we get the patterns, the really surprising patterns that we see on the surface of Sputnik Planitia, which is that left-hand lobe of the heart. I was not expecting to see anything this interesting. I'll admit it. I was looking for that, oh, I get to analyze loads of craters, and it's not going to be anything interesting, but you can see we have the dark patches, which we think are tholins, so kind of space gunk, reddish space gunk is how I've heard them described when nitrogen and other organic molecules, not biologic, just carbon containing molecules, are hit with UV rays, they can deposit these tholins on the surface. So we have that dark swath of tholins in total contrast to the methane and nitrogen ices that we see on the rest of Pluto. And the next day when we were coming in and we were about to see the downlink of the next image after close encounter, it was going to be zoomed in right on that heart. And it sounds like a spoilt brat to say so, but a few of us were not expecting very much. After the jaw-dropping result of this fail-safe image, we're like, oh, so tomorrow we get a picture of just an ice sheet. And so if we go on to the next sheet, the next picture, you can see what the ice sheet of Sputnik Planitia actually looks like. And like I said, I was expecting plain ice. I wasn't expecting to see this convecting nitrogen ice. So it's not convecting, bubbling in the same way as a pot of porridge or bubbling water would. That's convecting, but it's doing so really, really quickly. This is convecting over much slower years, thousands of year timescales. We're still working on the speed. And the redder blocks in this are tholin covered ice, water ice, icebergs that had kind of sheared off the edge of this massive impact basin and floated out into the nitrogen ice, which is Pluto's heart, Sputnik Planitia. If we go on to the next slide, it gives you a more of a perspective view. This next image is in enhanced color. So it's not bright yellow, it's not bright red. Those are helping us pick out the compositional differences. So the reds really show where the tholins are. That yellowy texture is where our nitrogen ice is. And my current project that is, I'm starting to do some 3D modeling with the IceAL hydrocode. And my job with the New Horizons team at the moment is to work out how deep the basin was after the massive impact that formed the basin that the nitrogen ice then settled into. That could give us an idea of how thick this nitrogen ice layer is. And that will tell us things about its rheology, how quickly it's convecting, things like that.
Wow, it's really, thank you for sharing these amazing images, and I have to say I'm really quite jealous that you've experienced this in your career. It must have been an absolutely amazing feeling. So I can see lots of questions are starting to come in, so that's great. Please, everyone, if you haven't asked a question yet, please do feel free to enter one in the Q&A. And if you can't think of a question but you see one that's already been asked that you'd like answered, please give it a thumbs up so we can make sure we get to all of the really popular questions. So Veronica, you've been talking a lot, but we've got, I hope you don't mind, moving swiftly on to these questions that are coming in. The first one, great question from Aidan, who's age 9, and so I'm absolutely delighted that we've got people here of all ages to be inspired by what you've done. He has noticed the rocks behind you and is inquiring, are they space rocks?
I do have a couple of meteorites. Oh dear, I dressed for Zoom, didn't I? Well, I do have a few meteorites in my collection up there. In the COVID time, of course, I couldn't be in my office, which has most of my space rock collection in, like a Mars meteorite sample and some globes that I can point at. But my house has my big rock collection. It does also include some impact breccia that you gave me as a present at the end of my thesis. So when an impact occurs, it not only has enough energy to melt rock, it also really fractures it. And so you get a lot of mixed up, sharp, angular pieces of rock, which then form an impact breccia. So I do have those. And then on the other side of me is one of my favorite Mars images of Nilipatera.
Yes, I was going to say you don't need any art. You don't need to buy any artwork when you're a planetary scientist, do you? Just print out the pictures that you look at during the day. Yeah, absolutely great. Was there? So there was another question by Kiva, age 11, who thinking about these rocks that are transformed by the impact, and I think inspired by that picture you showed of the swirling impact melt. Kiva's asking, what is the hottest recorded crater impact, and is it possible for a crater impact to be hot enough to vaporize rock?
Yes, I know that the impact melt that we've been looking at will have been thousands of degrees hot, and the impact is energetic enough to not only melt the rock but just instantly vaporize it. And it is one of the reasons that we don't often find remnants of the projectile on Earth. Like sometimes we're lucky enough to find shards of iron, but a lot of the projectile is vaporized on impact. So yes, good question. It does vaporize rock too.
Yeah, great question. So we've got a question from Steve as well, sort of continuing on this theme of what happens in these impacts. Is he's interested in recently formed craters. So have we been fortunate enough to see a crater happening now that we've been monitoring planetary surfaces for a couple of decades, with orbiters, so around Mars, around Moon. Have we captured before and after images of craters?
Yes, it's one of my favorite jobs with the HiRISE camera. There's another camera on board the Mars Reconnaissance Orbiter that isn't as high resolution as us. It takes pictures of a much wider area at low resolution, and it re-images the whole globe. And so it will find the sudden appearance of these dark spots. And so, Corrine, we do have a couple of pictures of these from like some of my Mars favorites. We are finding impacts that happen that we know are just months old. So let's move on from that one. Keep going. I think it's the next one. Here we go.
Oh, yeah, bang.
Yeah.
Big crater.
So this is one of my, oh, yes, thank you. This is one of my favorite images. And on the left, I've shown what my HiRISE image looks like. And so we have about 5 kilometer wide images and then 1 kilometer color image swath down the middle. And it's always very embarrassing if I miss and I get the interesting crater outside of the image swath. It doesn't happen often because we get such detailed coordinates from CTX, the context camera. And so it allows us to get these images of impacts that we know are just months old. We can't narrow them down exactly how many months. We just have that before and after CTX image that might be months apart.
Presumably this
hundreds. Sorry, Gareth.
No, I was going to say, presumably this helps us, understand, how frequently these events are happening on Mars, but also, of course, on Earth.
Yes, Earth has a thicker atmosphere than Mars, so a lot of these smaller impacts are filtered out by our atmosphere, luckily. So it's very useful to be able to look at the Moon and Mars to get an idea of what the flux of impactors are in the inner solar system. Yeah, we've found hundreds of these. Impact cratering is alive and well in the inner solar system, but they are small. Luckily, they're not dinosaur killers anymore.
Good to know. Good to know. Okay, great. So Lynn Belmar has got a couple of questions. So one of them, going back to Pluto. So would that have been an asteroid, a lump of rock, or that far out, would it have been something a bit different that caused the big heart-shaped sort of crater?
So I should clarify, the heart isn't all impact crater. It was only that left-hand side of the heart. We think that the impact occurred coming up from the south, created a kind of elongated crater, and then over to the side here there's the other lobe of the heart that might be the remnants of impact ejecta or something totally different. But in the inner solar system, most of the impacts that occur are asteroids. We're closer to the asteroid belt. We have a lot more rocky material, whereas in the outer solar system, it's far enough away from the sun for ice to condense. And so most of the impacts that occur out there are with comets and other icy bodies. So we think that the formation of the Sputnik-Planitia basin impact was probably a comet or another icy body.
Thanks, Veronica. So Jen Rowters has asked a question. So I think, going back to our discussion about how planetary science is a home for everyone, for people from lots of different backgrounds and lots of different sort of expertise and skills. Do you have any advice for people that want to get into planetary science, at all stages of life, but perhaps particularly at later stages?
So it did help me to bring my maths online and get better at maths, although that was my own personal struggle. And I know so many people that they never touched maths on their way in. Like they liked the chemistry, or, you know, they came to it from a different path. So finding out what might be needed for the job you want and trying to work on that is useful. But I think that what was most useful for me, getting jobs and getting collaborations going, is practicing the courage to just walk up and ask for things. Find out who you want to talk to, and then go up and meet them. I managed to get the data from the Galileo mission that I needed for my PhD by going to a conference that was being held up in Cambridge that I knew a lot of the American lot were coming to, and I hunted down the person that had this data and just, I don't want to say cornered him, although this exchange did happen to occur in a corner with me standing next to him while he was getting the data. But I also got into planetary science by walking into my relatively local observatory and just asking somebody there, how do I get a job in planetary science? And they directed me to UCL, where I did University College London, where I did some work experience and then did my undergraduate there. And even my high-rise job, I was coming to the end of my postdoc and I didn't want to leave Tucson yet, and I wanted to continue doing my research, but was also interested in the mission operations. And so I walked into Alfred McEwen's office and just let him know that I was interested and asked if he would consider me for any up-and-coming jobs. And there weren't any at the time, but because I did that, and I was very, very nervous. But because I did that, he knew that I was interested when a job came up. So my best bit of advice is go and talk to people.
Great, yeah, thanks. I think it's always good, you know, never be too embarrassed to go up and ask questions and introduce yourself. Yeah, that's great. So so you mentioned sort of before I sort of pulled you back to New Horizons, you mentioned that your new project to put a seismometer on Europa. Is that right? Yeah. So so Olga Joan has asked a question about why did you select that particular body? What is it? So we've had a seismometer on the moon, and very recently we put a seismometer on Mars, which is currently listening to Mars quakes and getting some fascinating data back from there. But so why do you want to send the next one to Europa?
It's to answer the same question that was part of my thesis, and that's the question: how thick is Europa's crust? And like we said earlier, that's important to see whether life could have evolved, and whether we can access that water there. And so it's quite a high priority for NASA to investigate where there might be life other than Earth in our solar system. We are developing a seismometer for any icy moon. So if the public interest turns suddenly to Enceladus, we can go there as well. But we're getting ready to hopefully be part of a Europa lander. And instead of me using the shape of impact craters on the surface to get a very, very rough estimate of how thick Europa's crust is, being able to land on Europa and listen to its seismicity, because as it goes around Jupiter, it gets squashed, and it gives I think it's probably always creaking slightly, and we can use that passive seismicity to record with our seismometer and get an actual reading on how thick that ice crust is above the water layer.
So we've had Lewis has asked a question. What do you think the chances are of finding life? That's a really difficult question to ask, and I guess it comes down a bit more to your I guess your belief more more than your scientific understanding. But yeah, what's your personal view on that?
I think the chances of finding life are slim. because we would have to be able to be looking for the right thing, and we don't really know what we're looking for, it's why we're concentrating on places that we know have water, is that all life on Earth needs water at least some of the time. But I'm not sure we'd find life. Me personally, I think that just based on the maths, the number of galaxies out there, the number of planets around stars, there should be life out there somewhere. I don't think we'll be able to make contact with it, depressingly, or maybe safely.
Let me ask a question maybe in a slightly different way. So Lynn has also asked a question about, evidence for life on Mars. So life on Mars or life on Europa, which one do you think is the more probable?
I think there's a decent chance of life having evolved on Mars during its past, when it was warmer and wetter there, because you'd actually have that water there at the surface, which life needs. So when I say life on Mars, I'm thinking about very, very basic microbes, bacteria. On Europa, if the water has been there for long enough, it's been there for longer, there might have been the opportunity for that bacteria, those single-celled organisms, to evolve a bit more. So I think on Mars, we have to be looking for past life, and on Europa, we might have a chance of finding current life.
So we've got another question. So Carsten, I think has picked up on you. So you talked a little bit briefly about your role in sort of selecting the places on Mars to take images of. So can you tell us a little bit more about that sort of process? What's the sort of typical timeline between you deciding that you want HiRISE to take a picture of something and that actually happening?
So I'm on cycle for HiRISE. So after I finish this call, I'm going to go off and make what we call our hit list, which is our HiRISE target list. And so the science team for HiRISE, they submit their suggestions for what they want pictures of. And we also have a website called HiWish, HiWish. And it's the HiRISE suggestion tool, where members of the public can go in, and if they want a picture of a particular area of Mars, they can go in and make that suggestion. And all of the public targets and the science team targets go into a big database of thousands of targets. And I'll create my hit list from those. I'll just pull a certain number from the database. And then I use spacecraft information that it plots out our predicted ground track over Mars, so that I can see which of those images are viewable. And I'm planning for 2 weeks of images, and it'll take me 5 weeks to plan the images and then make sure I'm getting the right image settings. So if I'm expecting a lot of dust, I need to make sure that I use certain camera settings so that I don't get too much glare back from the surface of these dust clouds. Or if there's frost, I don't want to have taken an image that overexposed, because then the image quality starts to degrade. So the whole planning process takes about 5 weeks. And then I send up my commands to the spacecraft, and it will then execute my commands. And for those 2 weeks, I'm the one taking pictures. And it's a really good opportunity for it's a good opportunity for everyone to get a picture of Mars, because then you could have that feeling of being one of the first 5 people to see that area on Mars, because we get the image back down, we validate that there's nothing wrong with it, and then release it. And as far as I understand, the suggester gets an email. So if you suggested it, you'll get an email and you'll be one of the first 5 people, or even less, to see this part of Mars. And it's an amazing feeling.
Yeah, that's brilliant. And then you can print it out and stick it on your wall. Fantastic. So yeah, I'm sure you're going to get a lot more requests from the audience today after that. So it's been fantastic talking to you, Veronica. I think we've only got time for one more question, unfortunately, but Veronica has very kindly agreed to answer every question that's been posted on the chat by email after this. So if we haven't managed to get to your question, I do apologise, but you will get an answer from Veronica. So stay tuned for that. But I'll leave the last question to the one that's most popular on this list now. It's from Andrew Shirley. Oh, sorry, it's from Melanie. So apologies for that. It's, did you ever want to go to space? And would you have gone if you had the chance?
I think pre-marriage and children, I would have gone to space if I could have been the first person on Mars, because then you'd get the first, the first to do something. But generally, I really like being able to breathe on my own without the aid of machinery. And so I prefer to have images sent back to me, and I'll let other people do the exploring.
Well, you are exploring in your own way, and I say I totally agree with you. I prefer to stay in the safety of my own bedroom at the moment. Okay, great. So thanks everyone, and thanks Veronica for the time and for kindly agreeing to answer all of the questions. To everyone that's tuned in for this Alumni Spotlight, thanks so much for coming, and I'm going to hand back now to Nicola just to say a few words to wrap up.
Thank you so much. Thank you, Gareth. Thank you, Veronica. That was a fantastic tour de force, and it was absolutely fascinating. I'm doing on a WhatsApp group as well, and somebody says that a friend child has been waiting for weeks to listen to this, so it was riveting. And we are planning one of these days, when life gets back to being able to move around, a trip to NASA. So I'm sure that will sell out fast. So I just want to share that there will be a survey link in the Q&As that we're sharing. Please do respond to our survey. That's really helpful. And a reminder that Imperial Plexus, if there are any leftover questions, Veronica will be responding to them on Imperial Plexus, and the recording will be available. So thank you, everybody. That was absolutely fantastic. We can only do this in this world. So, good luck, everybody. And I hope that you really enjoyed the event as much as we all did putting it on. Thank you. Bye.
Thank you.